So now you've messed around with your own free body diagram and perhaps either wanted to check your answer against mine, or weren't sure about your answer or how to go about the derivation, or you're taking the lazy route and just watching the instructor video right out of the gate. Guess I can't check any of those. But what does the free body diagram of this system look like? Well, everybody has different rules for drawing free body diagrams, but I'm just going to draw a little outline of my balloon, and it's at some angle because I'm assuming this is the situation where the balloon has been pushed over by the other balloon that's interacting with it. In this case, there are three forces that act on this balloon. So there is a gravitational force, and so again, everybody has different ways of labeling these forces. Modeling would actually probably just call this some force, label it generic F, that the Earth exerts on the balloon. Because the modeling preference, at least from what I've learned, is to identify the two objects that are involved in the interaction. There is also a tension force in the string, so that's a force up along the direction of the string. Again, some of us might label that T. I'm just going to stick with the generic F, but this is that the string is exerting on the balloon. And then I have a third force, which is a horizontal force in this case if I held the other balloon at the same level as this hanging balloon. And that would be a force that the balloon number 2 is exerting on balloon number 1, or I guess, I don't know, other balloon is exerting on this target balloon. And this is an electrostatic force, gravitational force, and a tension force. If this system is all in equilibrium, then Newton's laws tell me that all of these forces should balance with one another. But can we come up with an expression for finding the electrostatic force in terms of other things that we can measure in this system? Well, the electrostatic force must be equal to the horizontal component of the string force, the tension force in here, and the gravitational force from the Earth must be equal to the vertical component of that tension force from the string and the balloon. And if we assume that this string is out here at some angle, which I'll call theta, because all angles must be theta, I'm sure Isaac Newton declared that, we can write a couple of expressions in the horizontal and vertical direction that encapsulate what we were just talking about there. So I could write that the force that the string puts on the balloon in the x direction is equal to the electrostatic force that the other balloon puts on my target balloon. And I'm just going to drop the vectors. They're equal in magnitude and they're opposite in direction. And then the force that the string puts on the balloon in the vertical, which I'll call the y direction, has to be equal to the gravitational force that the Earth puts on the balloon. And then I got to use some trig. So if this angle is theta, this angle right here is theta as well, which means that this force that's in the x direction can get rewritten as the full magnitude of the force times the, let's see, I'm going to have the opposite of that angle, so it'll be the sine of the angle. Let me just erase on the fly here. So the force the string puts on the balloon times the sine of the angle is equal to the force the other balloon puts on the balloon in magnitude again. And then, let's see, we had in the y direction, y, that equals the force, the gravitational force the Earth puts on the balloon. So I'm going to similarly write that as the force the string puts on the balloon times the cosine of that angle theta. That's equal to the electrostatic force that the, rather the gravitational force that the Earth puts on the balloon. And here is where we want to do a little bit of algebraic sorcery. It's not really, but I'm going to divide this equation by this equation. So I'm going to divide this side by this side, divide this side by this side. What do I end up with as a result from doing that? Well, the force the string puts on the balloon drops out of the equation. I'm left with sine over cosine, and that is the tangent function. So I can write the tangent function of theta is equal to the force that the other balloon puts on the balloon, which is the electrostatic force, divided by the force the Earth puts on the balloon. Well, that's the gravitational force, so I'm going to replace that with the mass of the balloon times g. Most of us learned that as the acceleration due to gravity, but it's perhaps better called the strength of the gravitational field near the surface of the Earth. And then I can move that over and end up with the result that the force that the other balloon puts on the balloon is equal to the mass of the balloon times g times the tangent of the angle that the string makes. So as you're doing this experiment and watching the video, well actually doing the video analysis within Logger Pro, there's a way to write an expression, because in Logger Pro you'll know the mass of the hanging sphere, you'll know where you can look up g, and there's a way based on your measurements in the lab to figure out what the angle is and subsequently take the tangent of that angle. All those together will give you a calculated value for the force that the second balloon puts on the first balloon, or in the case of the video in Logger Pro, that the second little metal prod sphere puts on the first hanging metal prod sphere.